Okay, we'll get started. Just one check-in with you guys, see how things are going. How did your first homework assignment go? It's okay. Any questions, feedback? Okay. Yeah, it is a summer course, so things are accelerated, and I've just posted the second homework assignment, okay, and that'll be due next Monday, covering stuff that we cover this week, okay, and then next week is third week, and you're going to have a midterm exam next week. I mean, things just move very, very, very rapidly in our class. Okay, so just before we go on, I want to make sure we feel comfortable with the stuff we've covered. Okay, so the first day we covered inverse CDF method. Okay, so you create the you integrate the PDF to get your CDF, right? Or to get your cumulative distribution function, and then you invert that, and that allows you, because what the CDF effectively does is it maps from the domain of X onto the 0, 1 range, okay? And when you invert that, it then maps the domain 0 to 1 into the entire range of X. And so it allows you to go from a probability to a random value. So that's the inverse CDF method. And then on Thursday, we covered rejection sampling, which you have some kind of target density, target PDF that you want. And you, so here, let me just kind of just recap. So we have inverse CDF method. So the CDF goes from, something like this, and then the CDF inverse will look like this, okay? So this, the function goes from range of X, gets mapped to 0, to the range 0, 1, okay? And then this function, because functions, all they do is they map one set of values to another set of values, right? I guess this should technically be domain of X. Okay, so that's inverse CDF. And then on Thursday, we covered rejection sampling, which has, some kind of target PDFs, a target distribution that we are interested in. And maybe it looks like this, okay? And we'll say, maybe this is difficult to directly sample from. Difficult to sample directly, and so instead we have a proposal density. And what the proposal density does is this one is easier to sample from, and to accommodate for the difference between the proposal and the target, we say, for values in this range, we're only going to accept 50% of the values here, okay? So, values here are accepted only 50% of the time. Okay, so you propose a value according to the proposal density, and then you accept or reject them based on the ratio between the proposal density and your target density. Okay, and that's rejection sampling. And the hope was that the homework exercises gave you some practice with it and helps you understand what's going on. And if you have further questions, please ask. So before I move on to today's stuff, are there any questions on either of these things, inverse sampling or rejection sampling? Any issues that came up in the homework that you weren't sure of? Okay, then I will continue on here, and again, if maybe you don't have a question at the moment, but you have a question later, you're always welcome to come by office hours and stop by. Okay, so there's a few. Let's see if we can get into a couple topics for today. Okay. All right, and so one, we might call these convolutions, or this is basically a random variable is the result of a sum of other random variables. Okay, and so if you remember your Stats 100B, your mathematical statistics course, you should have learned about different distributions and their relationships to each other. Okay, and so here we'll start off with some easy ones. Okay. Wait, something just happened. Oops. Sorry. I think that was my daughter's artwork there. Okay, we're going back to here. All right. Okay, so we've got is the result of a sum of other. Okay, so let's just start off with the definition of the binomial distribution. So in your homework, I had you generate values from the binomial distribution using inverse CDF method, and this required you to calculate the PMF, and from the PMF you calculated the CDF, and then you had to invert that and probably use some vectors or while loops or something to go from 0 to 1 to this. Another way is we could have used the definition of the binomial distribution to generate random values of the binomial distribution. So how do we, let's say we have binomial I don't know what's going on here. Oh, I see. Okay, hang on. All right. Sorry, I have, apparently I have touch gestures. I had them turned on, so when I would brush with my hand, it would cause zooming in. Okay, anyway. All right, so if we have the binomial distribution with shape, with, what is it, size parameter, size m, and probability p, this is, okay. I apologize. Okay, so we've got the binomial distribution with size parameters m and probability p. What is this defined as? Okay, so x being we'll say x sub I comes from a Bernoulli distribution with probability p, which basically is what? Takes on the value 1 with probability p and 0 with probability 1 minus p, right? So we've got a Bernoulli distribution, which is basically a coin flip with probability p, and then the binomial is then defined as the sum of m independent x sub i's, right? So we would have S is equal to the sum from I equal 1 to m of x sub I, which will be, x1 plus x2 plus dot 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 up through xm, which will be binomial m and p, okay? And so we could generate draws from the binomial distribution on the computer in this way. Okay, and so you would say you could ask for, we will start off with U will be R unif, and we will ask for M R unif values, right? Okay, so this will give us M values between 0 and 1. And then how would we convert this into a Bernoulli? To be 1 with probability p, or 0 with probability 1 minus p. What would I do? I would just get x will be what? If I do u less than p, right? And this will become a true-false vector, and it will be true if u is less than p, which will happen with probability p, and it will be 0, or it'll be false if u is greater than p, which happens with probability 1 minus p. Is that okay? So this is, we have M random uniform. So now we have logical vector x with values 0 and 1. And we can convert this into zeros and ones. And then S would just be sum x. Okay? And so this will be binomial with parameters m and p. Okay? So that will be just one draw of the binomial. Is that okay? What if I wanted to have like n draws from the binomial? What would I do? Well, one option is that I could just throw this into a loop and have it run n times, right? I could just say for I in 1 through n, do this, and then each output it sums it up and does this, right? Another option, though, is I could use a matrix and some apply functions. So I could do a matrix of m by n values. Okay, so if I want 100 values, I could have 100 rows, each row having m values. Okay, so I'll ask for r_unif m times n, and I'll get a matrix. And then I apply the same logical thing. I'll ask, the matrix less than p, and that will turn the entire matrix into a logical matrix, right? Trues and falses. And then what do? I will just apply the sum function across the rows. Okay, so I can do, apply to the matrix sum, or you can also just do row sums. Row sums will also work, and it will turn the entire matrix, which is currently m by n, into a single column of n values. Okay, and you would get that. Okay, so that's another possibility. But this is it, right? So this is a very simple way to do the binomial distribution, and I think it's easier to comprehend this than the inverse CDF method for the binomial. You guys had to do inverse CDF for binomial, but maybe that wasn't too hard. And this is very simple. Fortunately for us, r_unif is not computationally expensive, so it's very easy for us. But you could imagine a time if generating random values, if that was expensive to do on the computer, then this would be not ideal, because you have to generate a whole bunch of these for this. Okay, is that all right? Binomial convolution. Okay. All right. Just a few other ones. So, you could have like the chi-squared distribution. And what do we have here? How do we define the chi-squared distribution? So we say z comes from what? Z will come from a normal distribution, 0, 1, okay? And then the chi-squared distribution is going to be the sum from I equals 1 to m of z squared, right? So this will be z1 squared plus z2 squared all the way up to zm squared. And this will be chi-squared distribution with m degrees of freedom. Okay, we have the beta distribution. You guys familiar with the beta distribution? So what's the domain of x for the beta distribution? It's so the beta distribution, you can think of this as basically probability distribution of probabilities. So this will, the domain is 0 to 1. So it's like, here's it could be something like, here's a bucket with a bunch of marbles in them. Some of them Some marbles are white, and some are red. And then we ask, what is the probability of getting a red marble? Okay. If you don't know anything about the bucket and you only know that it's either white or red marbles in there, and ask what's the probability of getting a red marble, you know that answer has to be what? Between 0 and 1. Okay. And then depending on what you see, you can then get a better idea of, oh, maybe the percentage of marbles is somewhere between 40 and 60%. Or maybe it's between, or maybe you're not so sure, and you say it's between 10% and 90%, and most likely around 50%. Or maybe you've seen a bunch of marbles, and you say, I'm pretty confident that the bucket's 25% red, maybe 26, maybe 24% red, okay? And the beta distribution is a way to express all of that, okay? So, these are, so potential beta distributions will look like from 0 to 1. It could also look like between 0 and 1, you could say, this thing. Okay, it could look something like this. Maybe you're confident that it's around 80% or something. These are all different examples of beta distributions, and they're all to represent, what you believe about the proportion or the probability of something. Okay, in this case, we're talking about what proportion are red. Okay, anyway, the way we can express a beta distribution as a gamma distribution is we can say, so the beta distribution has two parameters, alpha and, or we should say two shape parameters, A and B, okay? And we will say x1, x2, all the way up through xa, and xa plus 1, all the way up through xa plus b. These all come from an exponential distribution with lambda equal to 1, all right? And we know how to generate values from the exponential distribution using inverse CDF. Okay, so we can say all of these values come from the exponential distribution, and then y will represent the beta distribution, and this will, here you sum up the values I equals 1 to a of x sub I, and then down below you sum up all of the values I equals 1 to a plus b. Okay, so you are summing a subset of all the values you generated from the exponential, and this will come from a beta distribution with parameters a and b. All right, is that okay? Yes, question. No, some random variables are defined as what we say convolutions. Like some random variables are defined as, being derived from others. So, for example, the t distribution. I didn't write this, but how do we get a t distribution? you have a normal distribution divided by the square root of a chi-square distribution, right? With m degrees of freedom and things like that. And so, so you could use these definitions and say we've got the chi-square distribution, which, we're able to generate random normals using kind of the inverse CDF on the computer and things like that. So, I mean, the computer is able to do all of these random distributions for us. But, if we were in some impaired situation where generating random values from the chi-squared or generating random values from the beta distribution was not available to us on the computer, we could use their relationship definitions to get these things. Okay. Yeah, and there's like the Poisson and stuff like that. Okay, I think we'll end there. We'll do that for the convolutions. And of course, this requires you to understand the relationships between different random variables. Okay, are there questions on this? Okay. Kind of a further thing is we can generate maybe values from a random normal distribution, and from there we could go to a bivariate normal distribution. Okay, so we'll say if we can generate random normal distribution also get values from a bivariate normal. Perhaps maybe as an aside before we get into this, if we can generate from the standard normal, how can we go to a normal with different mean and standard deviation? Say first. Okay, so let's say zi's come from, well, z comes from standard normal, 0, 1, okay? And let's say x comes from normal with mean mu and standard deviation sigma. What's the relationship between x and z? Okay, so we'll let z equal x minus mu over sigma, right? So this is our z-score definition. Okay, and then, so if we're able to generate z's, yeah. Yeah, this is convention. Like, you could put sigma squared or sigma. x minus, this is okay, right? Okay, so you could put sigma squared or you could leave it out, depending on your convention here, okay? All right, so we got z is x minus mu over sigma. Okay, so then we will generate zi from normal 0, 1. So we'll assume that we can do this. And then to get x sub i's, let x sub I equal z sub I times sigma plus mu. And that's it, okay? If and then x sub I will then come from normal with mean mu sigma squared. So if you're able to generate from a standard normal, then we can go to any normal distribution. Okay. And now we want to know, can we go from a standard normal to a bivariate normal? Okay. So bivariate normal is a normal distribution of two variables that that might have covariance. Okay, so we could have might look something like okay, and if you look at, so this is x1 and x2. It would look like a normal distribution over here, and it would look like a normal distribution over here. But then, looking at the contours, there's obviously some kind of relationship between the two, right? Okay, so there is positive covariance between x1 and x2. What would it look like if there's no covariance between x1 and x2? So here we would say x equals x1 and x2, and x comes from normal, I should say, the vector x. Mu is equal to the vector mu1, mu2. And this is equal to sigma 1 squared, covariance sigma 1, 2, sigma 1, 2, and sigma 2 squared, right? And in this case, here, sigma 1, 2 is positive. This is the definition of the covariance, which is the expected value of the product of x1 minus mu1 and x2 minus mu2. So if sigma 1, 2, if the covariance is 0, what does our distribution look like? Basically, the things are perpendicular to each other. So they might not, you might get something that looks like this, okay? And so the axes here of the ellipses are you've got basically kind of these perpendicular axes indicating no covariance between the two. If no covariance, the axes of the ellipse are parallel to the x1 and x2 axes. Okay, so this is the bivariate normal distribution. We've seen this before, right? Or this is new to us? Like, I think it should have appeared in one of your other probability classes. Okay, all right. So you've got this. And so the question is, can we generate values from a bivariate normal if the only tool we have right now is to generate univariate normal values? Okay, so if we can generate z's from the univariate, can we get values from a bivariate normal distribution that, maybe has some covariance, okay? I mean, if there was no covariance, it would be very easy, right? You just generate some z's and convert them to x1s, and you generate some more z's and you convert them to x2s, and you don't have to worry about covariance because everything's independent of each other. So that's a rather straightforward thing. But the question is, we want to put in some kind of covariance between the two, and that suddenly gets a little bit more complicated, okay? So we will start with generating kind of independent normal values. Okay, so we'll say z comes from a bivariate normal with the 0 vector and the identity matrix as its covariance, right? So the mu is equal to 0, 0, and your covariance matrix, I should swap these two. So your mu vector is equal to the 0 vector, and the covariance matrix is the identity matrix. So basically, Z1 and Z2 are just standard normals, right? So if Z is equal to Z1 and Z2, Z1 comes from the standard normal, and Z2 comes from the standard normal, and Z1 and Z2 are independent of each other. This is so we'll start off with this, and then what we will do is we will let X be some vector B plus some matrix A multiplied by Z. I'll just say X is this, okay? And then so we want to find a vector B and matrix A so that X will come from a bivariate normal with mean sigma with mean mu vector and matrix covariance matrix sigma. Okay. All right, so we'll say this, and we will start off by saying, what is the expected value of X, and can we set the expected value of X to be equal to what we want, mu? Okay, and if we can, then at least our expected values will be taken care of, right? So let's find the expected value of X and then set that equal to our mu vector. Okay, so we'll say the expected value of X is going to be the expected value of B plus A times Z. Okay, and so this, what's the expected value of B? This will just be B, right? Because it's a constant. There's no variation there. Plus the expected value of A times Z, and this will just become B plus the expected value, of matrix A times the expected value of Z. Okay, and what do we have next? This will become B plus, what is the expected value of Z? It's 0. It's the zero vector. So we've got A times the 0 vector. So this will just become B. So the expected value of X is just the B vector. So we will set the B vector equal to our desired mu. Okay? And thus, the expected value of X will equal mu. Okay, that part was not too bad. All right, okay, and so now we'll do the same thing, but this time for the covariance. And what we want is the covariance of X, the covariance matrix of X, to equal, whatever we find that to be, we'll set that equal to sigma. Okay. So so we will find the variance covariance matrix of X and set it equal to our desired sigma. Okay, so we'll do sigma of X will be the covariance of X, which is the covariance of B plus matrix A times random variable Z. Okay, covariance of a constant is nothing, so this just reduces down to the covariance of A times Z. Okay, and so if you try to pull out a constant from a covariance term, what happens to it? Yeah, if it's univariate, you square it, okay? But it's a little bit more complicated with a with matrix form, and so we end up getting, we pull out the A in the front, and we have the covariance of Z, and we would have the A transpose out here. Okay, so it's a little bit different, but yeah, when you pull out covariance of kind of multi-dimensional thing, it gets pulled out like that. Okay, the covariance of Z is the identity matrix, so we get that, and this just becomes AAT. Okay, A transpose. So we have sigma sub X equal to AA transpose, and so now, and we want to set this, we will set this equal to our desired matrix, and now we must find A, so that AA transpose is equal to our sigma here. Do you guys remember enough linear algebra to know what we're supposed to do here? So a hint, sigma is a positive definite matrix. I guess it could be positive semi-definite, but if you have a positive definite matrix, you have the Cholesky decomposition. Maybe. Okay. Well, anyway. All right. Well, I'll give you the answer here. All right. So so what we have is, for any symmetric positive definite matrix sigma, okay, we can find a lower triangular matrix A, so that AA transpose will equal sigma, okay? And so we will let A be a lower triangular matrix, which we will call T11, 0, T21, and T22, and we want AA transpose to equal sigma, which will be our variance covariance matrix, right? Sigma 1, sigma 1, 2, our variance covariance, sigma 1, 2, and sigma 2 squared. This is what we have. Okay, so AA transpose will look like this. T11, 0, T21, T22 multiplied by the transpose. Okay, and so if we do this, we will get T11 squared, T11, T21, T21, T11, and T1 squared plus T22 squared. All right, and so we will set this equal to sigma 1 squared, sigma 1, 2, sigma 1, 2, sigma 2 squared. Okay, so basically I've got a bunch of equations. Yes? Why? Versus what? Oh, well, what we want to do is we want to, I mean, if we wanted to just find two matrices that multiply together to create this thing, there's infinitely many possibilities. But if we restrict A to be lower triangular, we can still find a solution, and it makes it our answer easier. So it's just kind of a trick using the Koleski decomposition, just so we can make our lives easier. Okay, so from this, we can then get a few equations, and we can say T11 squared is equal to sigma 1 squared, and thus that leads to T11 equal to sigma 1, all right? So we've got that, and then let's do another one, and we'll say T11, T21 is equal to sigma 1, 2, okay? And thus, now that we have sigma 1, we have sigma 1 times T21 equal to sigma 1, 2. So we have T21 equal to sigma 1, 2 over sigma 1. Okay, and then lastly, we've got T21 squared plus T22 squared is equal to sigma 2 squared. And so T21, this is sigma 1, 2 over sigma 1 squared plus T22 squared equals sigma 2 squared. So we get T22 is equal to the square root of sigma 2 squared minus sigma 1, 2 over sigma 1 squared. Is that okay? All right, and so if we use this, then we can get values to create a bivariate normal. So in recap, okay, so we'll let x equal b plus az. z is equal to z1 and z2, which come from a normal distribution of the zero vector and I, and then b is equal to mu1, mu2, and A, the matrix A is equal to and okay, so this is to generate bivariate normal random samples, random values. And it requires us to generate normal random values. Independent normal random values. Okay, so if we can generate independent normal random values, z, then we can then generate bivariate normal random values that have some kind of covariance. Okay, by applying a kind of a transformation to the independent random normal variables. All right, is this okay? So far we've just been talking ways to generate random values for different random variables or different distributions, okay? And again, the big picture of this in the Monte Carlo methods is that, you know, if we wanted to study the properties of some distribution without doing the integration to get the expected value or without doing the integration to get the variance, we can generate a bunch of random values and get and use those as a stand-in for the distribution to estimate the mean and estimate the variance or things like that. Get properties of the distribution there. All right, is that okay? Another thing we can do is Monte Carlo integration, okay? Or, you know, a way to estimate kind of the expected value of some sort of expected value of a function over a random variable x, okay? All right, so this is, so normally that would be one lecture, but because it's summer, we're moving on to our next topic here, okay? So just hold on, all right? Okay, so we've got, you know, Monte Carlo, this might be called Monte Carlo integration, but maybe just Monte Carlo estimation. Could be better, right? a better name. And the idea is x comes from some random variable, okay? So x is some random variable. And then the question is if we apply a function to x, what will be the expected value of that function, right? So what if we apply a function to x, what will be we'll say the expected value of the function. Okay? And is it just the function of the expected value? It's not, right? The expected value of the function applied to x is not the function applied to the expected value of x. So for example, let's say z comes from the standard normal distribution. And let's say we have a function is you just take the value and you square it. Okay? So what is the expected value of the function applied to z? What's that? This is no longer straightforward, right? So the expected value of z, what's the expected value of a random normal variable? 0, right? Random standard normal, the expected value is 0, okay? But the expected value of x squared of the function applied to z, that's not going to be 0 squared, right? The expected value of f of z is not equal to 0 squared. It is not, I should say it's not the function applied to the expected value of z. It is not f of 0 squared, okay? It's not going to be that. Do we know what this is? It's the expected value of a chi-square distribution with 1 degree of freedom, which, let's look up chi-squared distribution. It's just going to be 1, right? But let's see. Okay, so the mean just ends up being the number of degrees of freedom, but this is effectively f of x is effectively chi-square distribution with 1 degree of freedom. Which has an expected value of 1. Okay. But let's say you didn't know these properties. Okay. What would be the Monte Carlo approach to answering this question? The Monte Carlo approach would be, well, we know how to generate random normal values, so let's generate a bunch of random normal values. Then let's square them, and then let's get the expected value of the squared values. Okay? So we're not doing really any math, we're just generating a whole bunch of values, and we're using that. Okay? And that's basically what we so let's say this. Okay, so the Monte Carlo approach basically avoids any kind of actual math. Is, okay, let's generate a bunch of z's. Not yawns, but let's generate a bunch of z's here, and then let's square them. Okay, and then let's take the mean of the squared z's. Okay, let's square them or apply the function mean of function applied to z. Okay, and so we can verify what we already know, kind of empirically. Let's see if I can get this to start up here. Okay, so I'm going to just start off by saying z is R norm. Let's do 100,000 of these, okay? And I can just ask, what is the mean of z? And we get something close to 0, not exactly zero, okay? And then so we'll say f of z will be z squared. We're going to square all of those. And then we'll just ask for the mean of f of z. Okay, and we get something close to 1. And thus we say, what's the expected value of our function applied to a random variable? We would say our estimate is 1.00381. Okay, and that's good enough for me. Are there questions on this? Okay. So we're just getting an estimate, right? We could say, let's do, apply some other weird function. I don't know. Like if we raise it to the 4th power, what's the mean of this? Okay. The 4th power suddenly becomes 2.96, something like that, right? I don't know what I was expecting, but if we take our z's and we raise them to the 4th power, and we can see a histogram of fz. So it looks like that, right? So the histogram of z looks like this, but when you raise something to the 4th power, suddenly you get this very skewed right thing. And apparently the mean of this is around 3, okay? Most of the value is very much small, but then 394, right? What's the square root of 394? 19, and the square root of 20, 4.472, okay? So it doesn't happen very often, but if you end up getting a random normal value of 4.47, which could happen when you have 100,000 values, then you get 4.47, and when you raise that to the fourth power, you get a value like 400, and that's going to obviously skew your answer here. Okay, but anyway, so this is the Monte Carlo approach. We avoided any math. So somebody says, you know, what's your estimate? I wonder what happened if, I don't know, if I did a million of these things. Okay, yeah, we're getting something close to 3. Okay, so, you know, someone asks, what's the expected value of, you know, a random normal variable raised to the fourth power? Okay, I'm gonna guess 3. Okay, I didn't do any math. I just said, okay, I don't know. That sounds really hard to do, but I've got a computer. I generated a million random normal variables. I raised them all to the fourth power, and I took the mean of them, and I got something like 3. Okay, and that's probably going to be the correct answer, right? And if you did the integration, you'd probably get 3 as well. But you can imagine the integration for, you know, applying this function and doing all that math is going to be way harder, right? So this is the Monte Carlo approach. We're avoiding doing the integration. We're avoiding all of that. We just say, what's the expected value of applying some kind of function to a thing? Well, let's just try it out, right? Let's just generate a million values. My computer can do that quickly. Okay, obviously we can do it, you know, with more complicated things, and so so let's kind of do some kind of generalized form here, right? So what we want here. So this is kind of the generalized form, okay, is that we have a distribution so x is a random variable, x has PDF f of x, okay? X has PDF f of x, and we have a function h of x, okay? We apply the function h of x to the random variable x. And then let's say we want the expected value of the function h of x applied to random variable x, okay? Which is written like this. Okay, so this is the expected value of h applied to x, and then sub f, meaning it's applied over the distribution defined by f. Okay, and this is going to be the integral over the domain x So maybe that's negative infinity to infinity, maybe it's 0 to positive infinity, maybe it's 0 to 1, depending on what x is. And this is going to be h of x times f of x dx. Okay, so perhaps we have something like, maybe in the simplest case, we might just have a function and you just want to know the average value of the function over some interval. Okay, so maybe okay. All right, so our simplest case we have some function h of x. We just want to know average value of h of x over some interval, okay? So in this case, let's say this goes from A to B, okay? And we just want to know what's the average value of h of x over this interval A to B. Okay, so this is, so the average value would then be the average value of the function would be basically the expected value of h of x, okay? And x, the f here, is just a constant, okay? Because every value between a and b is equally likely, okay? So this is going to be the integral of x, h of x times f of x dx, okay? But this time, f of x is basically the uniform distribution from a to b, okay? This is just a constant. 1 over b minus a. Does that make sense? Okay, if we just want the average value of the function, okay, not and technically we're applying the function, but we're applying it to a constant. Okay, so it's not like where x is coming from the normal distribution or anything like that. We're just applying it to a constant, and we're just saying, okay, if we integrate this, then this will give us the average value of the function here, right? Okay, so this becomes relatively easy for us. Okay, this becomes we just do h of x times 1 over b minus a times dx, and so we can pull this out, 1 over b minus a times the integral. The domain of x is a to b. Of h of x dx. And so all we have to do is we just generate values from a to b. Let me copy this. That's not what I want. So we got okay, and so we will estimate this. Generating random uniform values from a to b, and then we apply the function h of x to the random uniform. And I'm sorry, we apply the function to the random uniform, and we'll take the mean sorry. Take the mean. Okay, and then we'll get, and this will be Monte Carlo estimator h bar sub n. Okay, n being how many values you used to generate this. Okay, so take the mean, which is going to be basically 1 over n times h of x super I. Okay, and this will be approximately equal to 1 over b minus a h of x dx. Okay, so let's do let's do a simple example here. All right. So let's say we've got the function so we'll go to Wolfram Alpha, and let's say I just want so we'll just try a simple why is my internet not working? Okay, is Wolfram Alpha working? Okay, so let's say we want the mean of x squared over 0 to 5. So we'll say our function is just x squared, and we want what is the average value over the interval 0 to 5. I mean, I guess we could do this by hand, but now I'm nervous that I'm going to make some kind of silly mistake here. So we'll say f of x is equal to x squared, and we want to know what is the mean of this function over the interval 0 to 5, right? And so this would become 1 over 5 minus 0 times the integral from 0 to 5 of x squared dx. This is the definition here. So I have 1/5 times, what's this, x cubed over 3 evaluated from 5 to 0. And so this will be 1/5 times 125 over 3. Is that right? 125 over 15. I don't know, what is that? 8.333 times 0. So what Wolfram Alpha said? Undefined. All right, 1/5 times integral of x squared dx from 0 to 5. Okay, I hope I did this right. We'll try this out here. Okay, and so so the way we would do this on the computer. So this is analytic, right? Okay, the Monte Carlo approach would say, I don't know how to integrate, which is kind of how I feel in real life. The Monte Carlo approach will say, all right, let's generate a bunch of x from random uniform, from the uniform distribution from 0 to 5. Okay, and then we apply h of x, x squared, to all of those x values we generated. And then take the mean of basically of all of those h of x's. Okay, least I hope. So Wolfram Alpha says it's 8.333, which means I didn't mess up my math. And then, okay, so we're gonna say X is gonna be our uniform. We'll ask for, let's say, 100,000 of these things on the interval 0 to 5. Is that okay? And then we'll apply the function x squared to all of those things. And then we'll just ask, what is the mean of all those? And it gives me 8.3126, which is a decent estimate. It's not perfect, okay? And we didn't expect it to be, because this is just, it's just stupidly going out there, picking random values, and trying to give us an estimate, right? Random uniform's not an expensive computation, so I can ask for 1 million of these things, and it gives us something that's a little bit better. Okay, I can ask for 10 million, and maybe that takes it took a moment, right? The computer took a moment to get those, and it's giving us something even better. We're not going to get any better than this. All right, but we'll ask for 100 million, right? 100 million random values from 0 to 5. Okay, so the computer takes a few seconds here. All right, that's 100 million values, right? That's a lot, okay? And we have to square them all, and we ask for the mean of all of those things. Okay, and it gives us something that wasn't any better than 10 million, okay? Actually, it's a little off now. All right, but anyway, that's what we get, right? And that was, okay. We applied the, when we did the math, we got this. All right, is that okay? So this is kind of Monte Carlo estimation. We can then, if we know the average value over the interval, we can also calculate the integral itself, which is going to be the area under the curve, right? All we have to do is we take the average value and we multiply it by the width of the interval, and we will get the area under the curve, okay? So, so h bar sub n, this is the Monte Carlo estimator of the average value of the function h of x over some interval, okay? And once again, here, let's, we'll say what we did is we generate x sub I from uniform A to B, and then we computed h of x for each generated x super I, okay, and then 3 is h bar n is 1 over n sum of okay, sample mean. Okay, and so this is the Monte Carlo estimator of the average value of h of x over some interval, and then thus the estimated value of an integral. So if we have I equal to the integral from a to b of some function h of x dx, okay, so this is the value of an integral, which is the area under the curve. This can be estimated approximately equal to the width of the interval, b minus a, times the Monte Carlo estimator, okay? So we just take the average value and we multiply it by the width of the interval, and that will give us kind of the total area under the curve. Okay, so this is width of the interval multiplied by the average value of the function, and this will equal kind of the area under the curve of the function. All right, is this okay? All right, so that's kind of the simplest case where you just want to estimate the average value of a function or estimate the thing. The general form is okay, so f of x is not uniform. This this works the same way. Okay, so the general form for f of x is not uniform. Okay, works pretty much the same way. Okay, and it's that so we desire the expected value of our function over some distribution f of x. Okay, and we apply this over basically the domain of that. Okay, and so x is a random variable with PDF f of x, and you know, it is assumed we can draw samples from f of x. Okay, so if we want the thing, this is we draw x1, x2, dot, 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 up to x sub n from f of x, and then we compute and then we estimate okay, and so this is pretty much the exact same thing, except this time f of x is not uniform, it just has a different PDF, and we're assuming we can get samples from f of x. Is that okay? Okay. So here's an example. This is all right. Estimate the normal CDF. Okay, and so this is. I know this sounds silly, but we're gonna say we want to estimate the normal CDF. Okay, we're gonna assume we can generate Z's from the normal distribution. Okay, so we're going to assume we can generate Z's from the normal distribution, and the question is if we can generate Z's from the normal distribution, can we estimate values of the normal CDF? Okay, and I know it sounds like, well, of course, but it's not actually an of course. Okay, because generating the normal CDF technically has no closed form solution, right? So we can't actually do this using an analytic approach. And so can we at least estimate this if we just have random normal values, right? So the desired value, the desired function to estimate is going to be defined as f of x, which is going to be the probability that z is less than or equal to some value of x. And this is defined going from negative infinity to x of the normal PDF dt. Okay, which technically is negative infinity to x of 1 over root 2 pi e to the negative t squared over 2 dt. Okay, that's what we have. And analytic approach is not possible There's no closed form expression for normal CDF. Okay, so we need to rewrite the integral from negative pi to x of 1 over root, negative infinity to this of x of 1 over root 2 pi e to the negative t squared over 2 dt into the form integral over some domain of h of x times f of x dx. Okay, where f of x is a PDF, and h of x is some function. Okay, and so technically, So we want to get our thing into this form here, okay? So how can we do this? Well, let's do this. Okay, so our original integral that we want is going from negative infinity to x of 1 over root 2 pi e to the negative t squared over 2 dt. Okay? So what we will do is we'll let f of z be the normal PDF. Okay? And then so the domain D is the support of z, which is minus infinity to infinity. Okay? So we want it in the form integral over the domain h of z times f of z dz. And so this is currently going from minus infinity to infinity of 1 over root 2 pi e to the negative t squared over 2. Sorry, let me leave it at z's. dz, okay? So this is what we have. Okay? So we've got this. We want this. Okay, oh, I'm sorry. And I apologize. I left off the h of z. Okay, so this is what we currently have, and we want to get this to be the equivalent, okay? So what we're going to do is we will use an indicator function for h of z, okay? And this will be the indicator that z is less than or equal to x, okay? Which will be 1 if z is less than x, and 0 if z is greater than x, okay? And so this breaks it down into 1 of x of basically the indicator function, z less than or equal to x of 1 times 1 over root 2 pi e to the negative z squared over 2 dz plus from x to infinity of the indicator function, z less than or equal to x, and this is going to be 0, 1 over root 2 pi e to the negative z squared over 2 dz. Okay? And so by using the indicator function, now we have basically what we want. 1 over pi, integral from negative infinity to x, the indicator, z less than x, times basically the normal PDF. Okay. So this gives us what we want. Okay, and so if we want to estimate estimates of the standard normal CDF, it can be done this way. We have okay, so we'll let h of z be the indicator function that z is less than or equal to x, and let f of z be the normal PDF. Okay, so what we do is we generate z1 to zn from the normal distribution. 2 is we'll compute h of z for every single z out there. So which is going to be basically 1 if z is less than x, 0 if z is greater than x, and then 3 is take the mean of h of z sub I. And that's it, okay? And that kind of makes sense. It's a very roundabout way of getting your normal CDF, but it would work, right? If you want to know what proportion, because the normal CDF of say 1.5 is the probability that a random normal value is less than 1.5. And the way we're going to estimate that is by generating a million values from the random normal, and then we basically say, is it greater than 1.5 or is it less than 1.5? And then we assign values of 1 if it's less than 1.5, zeros for everything else, and then we take the mean to get the proportion there. Okay, so this is an application of Monte Carlo estimation here, Monte Carlo integration, and we'll end here for now, and we'll see you guys on Thursday.